All right, let's get started.
Very good.
All right. Speaking of quantum mechanics, we need some external observer to verify our existence. And then once that collapses the wave function, then we'll know we're actually live. But until then, we're Schrodinger's interview. And where do you teach? You're in
Johns Hopkins.
Johns Hopkins. Okay, perfect. Yeah,
Right.
yeah. All right. And come on, somebody tell us that we exist.
We do exist.
We do. Well, we know we exist, but I think require some kind of external validation to know that this thing is actually working. This technology. I'm just going to take it on faith. I'm just going to assume that it
Right.
works. Very dangerous way to do a scientific experiment. Is take it on
Right.
faith. All right. All right, let's get started. Well, hi, everyone. I'm Fraser Cain. I'm the publisher of Universe Today. I've been a space and astronomy journalist for over 20 years, and most of the time I'm reporting news stories, but I like to bring you behind the scenes to see how I interview some of the researchers that are doing the work. And today I've got Dr. Surjeet Rajendran from Johns Hopkins University, and he's here to answer all my burning questions about what comes next in the search for dark matter and other stuff in this. Well, Dr. Rajendran, thank you so much for joining me today.
Thank you so much for having me on. I'm sure it'll be a fun interview.
Well, the question I always ask people is who are you and what do you do?
Okay. So I am Surjeet Rajendran. I'm a professor of physics at Johns Hopkins. I'm a theoretical physicist. So, in principle, I'm supposed to be sitting up there on a very comfortable chair like this and thinking of theories about the world. But I have sort of unusual interest in the sense that even though I like to be in a very comfortable sort of lazy boy, I believe that the only way we'll answer questions about the world is by doing experiments. And so I've been very actively involved in thinking about new ways in which one might perform experiments. What kinds of new technologies can one use to discover facts about the world? So I've been doing this now for about 15 years or so, and I've worked on a number of areas. For example, thinking about different ways to detect gravitational waves, different ways to discover new forces of nature, as well as quite a lot of more recent work that has been aimed at trying to find new ways to detect dark matter, dark energy, stuff like that. To me, that's very, very important because, the way physics has been working, right? Historically, it was a case that theory and experiment sort of right on top of each other.
Yeah.
And we would constantly have this very healthy mingling. But of late, that has been less true. And that's not good, right? Because at the end of the day, we want to figure out what's in nature by experiment. And that's always been my sort of main driving purpose.
Yeah, and it definitely feels that way, that the theorists have gotten ahead of the experimenters, and I don't know whether this has somehow stalled the progress of science, but definitely you can see some theories like string theory, supersymmetry have caught the fancy of the theorist community. And yet it hasn't led to a lot of really practical ideas on how to test these ideas. And so they have to remain completely theoretical. I mean, there's been some really interesting, I guess, side benefits from all this work in string theory, but not the advancements in our fundamental understanding of the universe in the ways that we're hoping. So how do you, I mean, again, as a theorist, it's a very interesting perspective for, essentially the experimenters are the heroes, you're the theorist cheering them on. How do you think about this then? How do you think that as a theorist you can bring this balance between the theorist and the experimenters more back in line?
Yeah, so the way this sort of has operated for me practically, right, is basically science is now very, very big, right? So many people are out there, they're doing their own thing, and they're extremely good at what they do. So, for example, many of the things that I've been involved in involve, I would say, rather novel applications of extremely precise sensing technologies. So, for example, there are these guys who call themselves, there's a whole field called AMO, sort of atomic and molecular optics, right? And these guys have worked extremely hard to create very, very precise instruments that can measure extremely small magnetic fields, very small accelerations, very small time changes. You may have heard things like atomic clocks, extremely precise instruments. And they're the pros, they're going to come up with the best way to make that measurement, right? But that's pretty much what they're actually experts on. By themselves, they don't know how these technologies could potentially have applications outside of their specific domains of interest. And what I have been pretty successful and I think had a lot of fun doing is sort of thinking about, well, how can we use a variety of these technologies to, say, discover facts about the world? So that's where I come in, because I think about a problem like dark matter. What do we know about dark matter? Very little. We know it exists, and we know that it's a new particle. It doesn't seem to be a modification of gravity. We roughly know a couple of things about its mass. You can ask, how heavy could the dark matter be? And the bounds are pretty ridiculous in the sense that it says if it's heavier than about 10 to the 24 grams, okay, that's if it's bigger than that, it's more or less like the size of a planet, and we would have seen that. So we know it's not heavier than that. And on the lighter side, it's something like 10 to the negative 22 electron volts, which sort of roughly, I don't know in grams what that would even be, more like 10 to the negative 40 grams, something like that. So there's an enormous range of masses that the dark matter could exist. That's what all we know about the world, right? So I've come to this perspective where I say, look, the range of possibilities is so huge. How can I think about systematically probing large parts of this parameter space, as opposed to saying, hey, I like this one theory, and I'm only going to go and test that one theory, right? Somehow that has been the attitude of the community. And, to be fair, that used to be the attitude of the community. People were like, they were very convinced because of these mathematical reasons. They were like, supersymmetry predicted a specific kind of dark matter particle, the WIMP, okay, the weakly interacting massive particle. And people were extremely focused on finding that one particle and nothing else. So I come in and say, well, why? Why are you so convinced that I have something like 60 orders of magnitude in mass that you think the answer is this, right? To me, that sounds kind of crazy and confident. And I'm like, look, we don't know anything, so we should be looking broadly.
It almost sounds like it's a bit of a Hail Mary that they've because the math in the supersymmetry or string theory or whatever predicts a particle, you might as well try to see if that particle is there. And if you're done, then you get to roll up all of the excruciating work that it's actually going to take. But since that Hail Mary didn't pay off, now you got to do it the hard way. And the hard way, I guess, is not confirming what you think you know. It's disproving everything else until you're left with whatever remains that still fits within we don't know what dark matter is, but it has to be within this range of mass. So if you take that kind of holistic view, what is the best way to kind of hew away all the rock in this, or the marble in this statue, in a more effective way?
It's an interesting kind of question, right? Where basically, when I've advocated this point of view, people will go and tell me, like, sort of, and this was more true about 10 years ago, where people will be saying something like, well, this guy simply wants to go on a fishing expedition, right? Because that's what I'm doing. But I have the point of view, I am going on a fishing expedition because we know there is some fish out there. That's the dark matter. We don't know what kind of fish it is, right? So it could be an extremely big thing like a blue whale, or it could be some very tiny little Finding Nemo style fish. So the job is to really figure out what kind of nets can I actually construct, which are able to go and find these varieties of fish, right? So if I use the kind of net that I need to catch a whale to try to catch Nemo, it won't work. So what I do really is to think about it systematically, but I say, look, if I think dark matter is in this range of mass, okay, say this range of fish size, what are broad properties it could have? And once you think about it that way, you realize, well, look, what are we trying to do, right? We're saying there is some dark matter particle out there, and detecting it means we want that particle to change some detector that we build out of atoms and light and stuff like that. So then you say, what are some general ways in which various classes of particles could affect atoms and light? Turns out there aren't that many ways of doing them. Okay, so just to give you a simple example, if you think dark matter is extremely low mass, right? So yeah, and actually, like, here's an important point about it. We're talking about two very extreme ranges, right? Like extremely light dark matter and extremely heavy dark matter. Now, here's one fact we know about the world. We know how much dark matter energy density there is, the total amount of dark matter energy we know. So if I think about the dark matter having a very, very small mass, because its total energy density is fixed, there has to be a large number of dark matter particles, right? So when we think about trying to detect extremely light dark matter, the way you want to view this is like a lot like how you view wind, right? So when you have wind is the fact there's a large number of air molecules that are moving past you. How do you detect wind? You could think about two ways of detecting wind. One of them will be efficient, the other will not be. So one way of detecting wind may have been for you to figure out if every single, like trying to figure out the energy deposited by a single wind molecule, right? You could think about a detector that way. That will, of course, be very hard because the wind molecule is so light that it doesn't deposit that much energy. So the way you detect wind normally is that you build like a windmill or a wind vane or whatever, where you're looking for the collective effects of all of these huge number of wind molecules coming and hitting you.
Right.
Right. So in the ultralight dark matter case, that's kind of what you want to do. You don't want to look at the amount of energy that can be deposited by a single dark matter particle. That is more appropriate for heavy dark matter. But for light dark matter, because there's going to be a huge number of dark matter particles, you want to look for collective effects of these things. Right?
And that collective effect could be seen at small scales or even large scales.
Yeah, they could be seen. In fact, a lot of the work I've done is what is called small scale experiment, which basically is the idea that these collective effects can come to detectors that you have in your laboratory, and you can see their effects. So I would say there are only about 4 or 5 of these collective effects, and I can list them all.
Yeah, please.
So what can the dark matter do, right? So you have this wind of dark matter, and you're asking, how can the wind affect particles in the world that I control? Things like neutrons, nucleons, electrons, photons, things of that kind. So what can this wind do, right? So this wind can come in, it can produce a photon, it can produce some light. One can go look for that. This wind can come in, it can drive a current in a circuit, it can push on electrons. One can go look for that. This wind can come in, and if you have a spin of, say, some electron or a proton or whatever, it can make that spin move back and forth. So you can look for the rotation of spins caused by this wind. It can also directly push on bodies. So if I have a mirror hanging somewhere, this wind can come and push on this mirror. Okay? And the thing is, we as humans have now gotten extremely good at measuring these effects. So for example, if the wind pushes on mirrors, what you're going to be doing is a lot like this experiment called LIGO, which looks for gravitational waves. So they're looking at like extremely small motions of these mirrors, right? So you could pretty much use the same kind of technology to look for small motions of these mirrors where the motion is being caused with the dark matter wind pushing on it. Humanity has also gotten very, very good at measuring small magnetic fields. So if the dark matter came in and let's say it created a small current in a circuit, that small current will also create a small magnetic field. And you can use that signal with a very powerful magnetometer to measure that. If the dark matter comes and makes some spins wobble back and forth, as the spins wobble, they also change their magnetic field. And you can use a very, very precise magnetometer to measure that small change in the magnetic field. Right? So that's kind of how I think about it systematically.
Right. And so then if you set up these experiments, you created, you set up 4 big experiments side by side, one with the mirror, one with the magnetometer, one detecting electric current, etc. And you didn't detect anything outside of, I guess, the cosmic rays coming through or, all of the phenomena that you already know and can account for.
Yes.
What would that allow you to do in terms of your understanding of that space, that search space for dark matter?
Yeah, this is a very tough question, right? Because in a sense, this is one of the problems of the dark matter search business is that you don't know how far you need to go, right? So basically, what we are learning is that if you don't see anything, you're basically saying, well, the dark matter is not this kind of particle with this range of interaction strength. right? So that's what we're looking for. We're looking for a dark matter particle at a certain mass and a certain interaction strength. And if the interaction strength is too weak, I cannot see it. So there could still be a dark matter particle out there. It's just that you require more and more sensitivity to get down there. And if we as human beings don't have that level of sensitivity right now, we won't be able to find it. So it's a tough game, right? But basically, like it's a thing where there isn't a clear sign of saying stop now. This is a waste of time. That's just not true. You kind of just have to keep sort of digging in. So I would say it's a tough problem because you need to go both in wide in mass as well as deep in coupling.
But aren't we? I mean, aren't physicists already doing this process? I mean, when we talk about dark matter, we no longer we know that it's cold dark matter. And so we know that it probably isn't hot neutrinos because of various constraints. So, right. And as you already mentioned in the beginning, the mass constraints that dark matter could be, there's possible cross-section sizes and so on. And then, of course, there's a whole other field of MOND. How, I guess, do you feel like physicists kind of got halfway there by sort of figuring out that it's cold dark matter and then have been continuing to search for the right particle as opposed to just giving up to not knowing or giving in to not knowing and then just working on constraining it before trying to identify what it is?
Well, I think it's very difficult to make better constraints than what we have, right? So in some sense, the difficulty with dark matter is that so far, we've only known about its existence via gravity, right? That's how we know there's dark matter. And gravitation is not a particularly powerful force, even though it dominates the overall structure of the universe. The constraints you get from gravitation are somewhat pretty weak, right? So that's why the parameter space is so large. And so this is a psychological thing about humans, right? So when they see the parameter space being so big, people have a tendency to psychologically say, look, I am so convinced it must be at this point X, because the idea of searching over this broad range of parameters scares people, right?
But I don't see
kind
the
of
searching,
feel like they
I
should
guess.
put these constraints, but these constraints are in some sense kind of artificial because they're not actually based upon anything like truly real, right? So all you can ever do in some sense is basically constrain a certain model. That's all you can ever do, right? Until you find the thing. So you kind of have to be comfortable with that fact that the parameter space is so huge that you want to look broadly.
But I think that process of constraining the search space would be helpful and appreciated to know where to look. It's kind of like you drop your keys in a parking lot and you don't know where to look. But if you can somehow start to figure out where you walked. So why don't you start there? Then you've constrained the search space. And that is very helpful. And I can see this balance between constraining the search space and then taking your shot and think, okay, this is it. And the experiments created, like when you think about the complexity and amazing sensitivity of something like LIGO, which many people didn't even think was going to work. And when you understand the physics involved in that experiment, it's mind-bending.
Absolutely.
What kind of a leap of faith, or I guess, would it be worth it to create a machine that complicated and that sensitive that's only job is to tell you where not to look?
Very good. So there are two very important issues that you brought up, and they're both extremely central to this philosophy that I'm advocating in terms of how to do this, right? So first of all, you mentioned this thing about the parking lot, that you dropped your keys, and you obviously, if you knew where you walked, it makes sense for you to go and search where the on the route that you walked, right? That makes sense. Now here is the real story for dark matter, right? So it's something like the following. You know that you drop your keys somewhere on planet Earth. That's all you know, right? That's this huge space of parameters. Now, of course, it's very, very difficult to go and search entire planet Earth. So instead, what you do is that you go and talk to an astrologer who tells you, hey, due to this weird set of beliefs that I have, the dark matter must be in Maryland, right? Of course, you then feel better about going and searching in Maryland because the astrologer told you that's where it's supposed to be. But it's not really based on anything, actually factual, right? So the thing about physics is that we have to confront the problem at hand. The problem at hand is that this is an immense effort. It's extremely hard to do, right? So we can't make progress unless we're intellectually honest about what is known and what is not known. The second thing you brought up is also a very important question, which is that would I advocate that people spend the amount of money and time that it took to find LIGO, to build LIGO, to go after any specific kind of dark matter particle?
Well, not go after any specific. Oh, I'm saying just constrain the search space. Its job is not to find particles; it's to tell you where not to look.
Yeah, but the thing is, right, what I'm telling you is that this idea of knowing where not to look is pretty hard because it's so little is so all the time, right? We basically say if there are particles of a certain kind, those particles would have been, produced in stars in certain ways. They would have shown up in our colliders in some way, right? So we do put in those constraints. It's just that they're not that constraining.
Right.
It's like saying, for example, that you knew you dropped your keys somewhere on planet Earth, not the solar system, right? So there's certainly, when you lost your keys, yeah, you don't have to search the entire universe or the entire galaxy, but it's still planet Earth. So that's what I'm telling you, that the constraints are loose enough
right.
that you are kind of in the situation where you still need this rather broad program. But the point is this, right? That let us say, theoretically, this could have been possible. Suppose every single dark matter mass that I want to search for, if it required several $1 billion of money and 30 years of people's efforts, would I be advocating that we search for all these dark matter particles at the same time? But even if I advocated it, it's not possible, right? There are only so many physicists in the world. The physics budget is whatever it is. So you can't be searching for all of these things at the same time. But that's not true. What's true is that each of these experiments typically cost about a few $1 million, and it requires a few groups, maybe like 10 to 20 people working for maybe 10 years to kind of substantially dig in, right? So I kind of view this balance in the following way. If you were going to spend billions of dollars of money and 30 years of people's lives, you better be goddamn sure that the thing that you're going to search for is actually there.
Like the Large Hadron Collider, like
the LHC,
built
right?
to
like
find
the Higgs was definitely going to be there. It was certainly worth it, you spending 30 years and billions of dollars going after the Higgs. Same with LIGO. LIGO made sense because you knew there were these gravitational waves at some level, right? Okay, they had some slop about maybe a couple of orders of magnitude. They don't exactly know what they would be, but you were guaranteed that if you could make the technique work, which of course was unclear in the beginning, but you knew that if you could spend that $1 billion and get it down there, you would see something. That's not true about dark matter, right? There is no dark matter particle where anyone is convinced that all you need to do is spend $1 billion and 30 years of effort and you are going to find it. If there was such a dark matter candidate, I would be all for it,
of course.
But that's just not true.
Now you started originally talking about how we might search for light dark matter.
Yeah.
Do you have sort of a similar set of thinking about much more heavy dark matter?
Yeah, I do actually. So this has more been my more recent interests. So I spent a bulk of my career thinking about the ultralight dark matter sector. But more recently, I've been thinking about extremely heavy dark matter and how one could actually go and find it. So there are, again, different classes of these guys. So the challenge with heavy dark matter typically is the fact that the number density is so low now, right? Because again, the total energy density is fixed, as we said. If the mass of the dark matter gets very, very heavy, the number of such dark matter particles gets extremely small. So you run into the following problem that I, as a human being, can build some detector on my ground. It's typically a few meters in size if I get very aggressive, and I can operate it for a year. So all I can ever do in my experiment that I build on the ground is wait for a dark matter particle to go through it. But the dark matter is so heavy, right? It may never go through an experiment that I build in 1 year, right? Because it's just so rare that it's so hard for me to find it. The question is, what do you do in that case? What kind of strategic thinking can you actually have? So I've been exploring sort of two possibilities. One is that it does something dramatic to an astrophysical body, like a star. Okay, so one of the works that I was involved in, it was kind of a cute idea that basically it turns out that for certain kinds of dark matter particles, like primordial black holes, these are extremely heavy objects. These things can go through like white dwarf stars, like these stars that we have around us, and they can actually make them blow up into supernovae.
Wow.
Okay. And it's a crazy thing because it turns out that a white dwarf is essentially like a nuclear bomb waiting to explode. It's got all these carbon nuclei all sitting next to each other, and the carbon wants to fuse. But what's happening is that in a white dwarf, the temperature by itself is so small that the carbon does not undergo fusion because it has to go through this, fusion barrier, right? Fusion is very hard. But what can happen is that when these very, very heavy dark matter particles go through, they can heat up a tiny part of the star to very high temperatures. And that then makes the carbon over there undergo fusion. And then all the energy released in that process can then go nearby to heating up other carbon atoms, making the whole thing explode like a bomb.
Right. Okay. And I guess it's similar to the way like a type 1a supernova goes off.
Exactly.
Because you've got a buildup of material on the surface that chain reactions across and just blows the whole thing apart. But it has to be
It's a very similar process.
Right. Okay. That's really interesting. So, So that's one way. Are there some other places that you might be able to see them?
Yeah, so I've kind of recently been involved in a very fun project with a group of guys at Harvard, the University of Maryland College Park. Basically, the idea is that, one of the issues we ran into was that, look, if I build some detector that's a meter squared in size, and I operate for a year, that only, certain massive dark matter particles can go through. How can I change that? Well, one thing I can actually do is I can leverage the fact that the Earth is very old. So let me go and look at some very, very ancient rock. Okay. So that means this rock has been around for about 1 billion years or so. And what you can look for is basically as the dark matter went through, it could have left unusual tracks in the rock. Okay. So the idea is basically that basically let me go and look at a meter squared of rock in actually the Jack Hills of Australia. That's our place where we think this is the best place to do it. So they have all these ancient quartz in that area. And if you have very, very heavy dark matter going through, it'll basically create this very, very long line of damage in the rock. And people these days have very fancy ways of imaging rock, with all kinds of fancy technology. So the idea basically is for us to get a very old piece of rock from these hills and image them and see if there are these very unusual tracks in the rock.
That's really neat. What would be even better would be a chunk of the moon. I've heard, I saw a paper, someone talking about how the moon is like the perfect place to get a historical record of essentially cosmological events in the universe, that you will have written in the regolith every supernova, every gamma ray burst, everything that's happened relatively nearby over the course of billions of years. You just take a great big core sample, bring it home, and then slowly pull it apart bit by bit. And you would be able to sort of roll back. But I can imagine taking a cubic meter of the moon and bring that home, and then you'd have something that wasn't affected by various Earth creatures and so on. That's really neat. What about sort of stuff that's in the middle? So you've on the one side you're detecting en masse this wind, and on the other hand you're detecting giant particle events, primordial black holes passing through your planet and so on. What about the stuff that's in the middle?
Yeah, the stuff in the middle is also very interesting, and I've kind of thought a lot about. So it's an interesting problem. So the traditional community, the people who do what is called weakly interacting massive particle dark matter or WIMP dark matter, these guys they're in the middle in many ways, and they've actually done a lot of very important work. And so what is now true is that the sort of conventional, I wouldn't even call it conventional. I mean, because they've been pushing the envelope on it continuously. It is now possible through a lot of very hard work by the community to detect something like the dark matter comes and hits something, let's say, or gets absorbed and deposits about an electron volt of energy. Okay. Now, 1 electron volt is something that we in particle physicists, we use it all the time as though it's a very large number, but it's not. It's like an incredibly small amount of energy. It's like 10 to the negative 19 joules, a very, very small amount of energy. So they're actually so good now at measuring these very, very small 1 electron volt amounts of energy deposition And the reason why they can do that is because when the dark matter deposits that 1 electron volt of energy, it can typically ionize particles, okay? And the way that works is that, how do you see a small amount of energy? Fundamentally, you want to create what I would call as an amplifier, right? You have something that deposits a small amount of energy, and that's very hard to see, so you need to increase its effects. So one way in which these guys do this is basically they will apply a large electric field, let us say, and something comes in, it hits something, deposits some heat, and that causes something to get ionized. Okay, some electron gets ionized. Once you have this electron getting ionized, you put a large electric field, that ion now gets pulled up at very high energy, and they can then see that. So they fundamentally amplified the effect of the dark matter. The difficulty with this approach is that you have to be able to deposit enough energy to ionize objects. And in our world, there is a minimum amount of energy you need to ionize. They're about 0.5 eV, something like that, like not that much below an electron volt. So to go below that, you require newer ideas. And what I've been involved in is sort of an interesting field called single molecule magnets. And here's kind of the idea. Okay, so as a cartoon, here's how it works. Imagine I take a bunch of spins, like in a magnet, and I apply a magnetic field in the opposite direction. So the spins are all aligned in one direction. The magnetic field is in the opposite direction. What that means is basically that these spins are not in their ground state. They're not the lowest energy, right? They're excited. They're in the wrong direction. They're anti-aligned. So if they flip, they'll actually be able to release energy. But you can create materials where the spin is anti-aligned. So, right? So there's a stored energy in that system. What I was thinking of was basically that, well, maybe something can come and hit those spins, deposit some heat. And when you deposit that heat, the spins that absorb that heat, they jump to the ground state. They flip. Mm-hmm. And when they flip, they release energies that they've stored in them because of their excitation in the magnetic field. And that energy can then go and cause the nearby spins to also flip.
Right. Okay. I see. But so, like in general, though, you're essentially taking, again, some volume of shielded volume, hopefully below the surface of the Earth or whatever, and you are measuring the entire energy that is in that area, and you're looking for anything that's out of the ordinary that is essentially some kind of interaction from a medium mass particle that's coming out. And
that's right. And
the challenge is that our ability to multiply the detections is a certain minimum, but if we could develop more fundamental ways of multiplying the whatever interactions are happening, then that allows you to search a lot deeper and detect far more sensitive events.
That's correct. Yeah. So the challenge is really in this game, in the middle, is about trying to detect smaller and smaller amounts of energy, right? So you need better and better amplifiers. And what I've been involved in is sort of ways in which the conventional amplifiers are based upon using electric fields and ionized material. And I've been trying to do that on the magnetic side. Simply because the amount of energy it takes to cause these magnetic spin flips is a lot lower than what it takes to ionize an atom.
So then let's put it all together. So at this point, you've got sort of some ideas for the lightest particles, some ideas for the middle particles, some ideas for the heaviest particles. Right now, science is facing, do we invest in what comes after the Large Hadron Collider, the superconducting super collider, and it's, the goal is to essentially just to smash particles at random and see what happens and hope that something is in there, which feels like that's still part of what you're describing, just in a very expensive way. How would you apportion funds at this point to try to make some meaningful progress in the search for dark matter?
Well, so the dark matter game is a lot cheaper, of course, than building a collider, right? So as we said, these are a few $1 million experiments, and they only require maybe tens of people working for maybe 10 years, right? So there's a lot cheaper than what is being done for the next collider. The collider is basically tens of billions and decades of work, right? So as far as the dark matter game is concerned, I think, the community has, by and large, I think, embraced this approach. that maybe a decade or something ago, when I was beginning to do this, the community was extremely focused on a small number of experiments. But today, in fact, there are a number of people around the world who are actually coming up with their own ways of detecting dark matter. I mean, I'm not the only guy in this game. There are plenty of people trying to do this. And many of those experimental efforts are also funded. Simply because, as I say, right, this is one of those things where it is not that that resource intensive for any one person to do. Plus, there is a feature that sort of sociologically, right, the LHC thinks that these are like large experiments. You know, they are, and when you have a large experiment, there's a lot of management involved, and you know, people feel constrained, I think, sociologically in terms of what they can do, what they can play with. Here, you're kind of in a situation where people who are more independently motivated are able to get into the game and do meaningful things, right? So you can be your own person trying to do your own kind of thing. And so there is that element of it attracting, I would say, the more small-scale entrepreneurial side of physics, where people who want to play with their own technology, you know, are able to get into these things, right? So, so that way, the investments can be, I would say, fairly broad, and it's not too intensive for any one person.
It's, I mean, I totally agree with you. You know, when I think about our reporting, you know, we're talking about various interesting tabletop experiments being done in the search for dark matter, or relatively small, something set up in an old salt mine, or which, as you say, you know, is sub $1 million or a few $1 million expense. A few people, one researcher and a few grad students are often not reporting. You know, they're all saying we didn't find anything, but still are helping to constrain that search space. And so does it feel like, when I sort of think about, like, you could set up your mirror or whatever, and you could set up to a certain level of sensitivity, and then you could run that experiment for a year and you would find no result. Yes. But if you had made a bigger mirror and a more sensitive mirror, maybe you could find a result next time around. And so it's sort of iterative.
Yes.
In that. And it feels to me like one of the things that scientists don't like to do is to report a negative result. Does that, and you know, it's like you want to say that you found something. You don't want to say that you spent the last year and you didn't find anything, even though finding nothing is incredibly important to constraining its parameter space. Do you think that limits the way scientists work at all?
No, not really, because here's the thing that I learned, right? Which is that when it comes to experimentalists, and like one of them was very blunt with me. He basically said, look, Surjeet, all you are doing is giving me excuses to play with my toys, right? So these guys love to build these really, really sensitive instruments.
Yeah.
And I'm just giving them an excuse to get in there and, like, you know, play with all the tools that they have to make more and more precise experiments. So it's, you know, I agree, right? People would have, I mean, everybody wants a discovery, right? That's what that's really what we're trying to do. But it's not like in this game, especially, again, as I said, right, it sort of attracts a certain kind of person who's willing to go in there and play with these things, right? Like, that's kind of what they're really excited about. And so for them, sociologically, I have not really found it too difficult to even motivate people to do this, because most of them do know. I mean, pretty much everybody does know that most of the time they're going to be reporting a null result, right? Yeah. It's still a meaningful result, as you say. It constrains something. It tells us what we don't know. I mean, you know, that we know that the dark matter is not particle X, right? We know that. So that's, of course, meaningful. But ultimately, I think what motivates them is just the fact that they love the technology, right? They just love playing with it.
So what if we had a Nobel Prize for null results? Right?
That would be a very easy Nobel Prize to get from many people.
Well, but I spectacularly null results, right? Like somebody who went above and beyond the call of duty to not find anything. And
right. So actually, there's an example of such a prize. It was given to, it's not for the Nobel Prize people, but this Breakthrough Foundation. So they gave this Breakthrough Prize, which is like $3 million, to this group at the University of Washington. So these guys were basically trying to figure out if the force of gravity is exactly like what Newton had predicted, down to like the scale of like a distance of a micron. Okay. So, you know, we know gravity works very well at big distances. You know, that's kind of been measured. It's possible there are deviations from the law of gravity at shorter and shorter distances. Of course, they didn't find anything, but it was really heroic effort to actually get down there and show that gravity does work like how you think it's supposed to work.
Right.
And
Right.
that heroic effort was justifiably recognized by this very nice prize that they got. So there are similar such adventures that I think people do. Like, for example, for a long time, we have been engaged in a game of trying to see if the electron has a dent in it. So, this is called the electric dipole moment of the electron. And for 50 years, humanity has been trying to find this little dent in the electron, and we haven't found it yet. And the experiments have gotten more and more and more heroic. They have required more and more and more technology. And these guys have really been, pushing the envelope on this regularly. So I think, it is heroic effort, and in my opinion, it is certainly worthy of all the recognition that I think that requires.
Yeah.
Yeah.
And because it really feels to me like it is as important as the people making the discoveries. If you've removed every negative possibility,
Right.
what remains, could be interesting.
Yes.
So then it sounds like partly this is a technology issue. So from a sort of like an engineering standpoint or a funding standpoint, how could we get these people better tools?
Right. So in terms of, like, I would say funding, right? It's an interesting sort of thing that you land in there. So here is a fact about the world, right? So a lot of our money for how research gets done gets apportioned by government grants. Yeah, so the technologies that we talked about, right? Things like basically measuring very precise magnetic fields, measuring very small accelerations, very small time changes, things of this kind. Traditionally, the funding for this comes from organizations like NIST, right? The National Institute of Standards and Technology, because they're interested in creating very, very precise measurements. So they'll give you money to build a really good clock, for example, or a really good magnetometer. But they don't per se care about trying to find dark matter. That is not part of their government remit. Right? Finding the dark matter is supposed to be the job of the Department of Energy or the NSF or people like this. So traditionally, it has been the case that, and it's an interesting challenge, right? Because first of all, these guys have to be able to demonstrate that they can actually build a really good clock. I mean, without a good clock, you can't do any of these things anyway. But once you've got a really good clock, there's an extra amount of effort you need to really try to use it for dark matter, right? Because there are a lot of extra technologies that are required to make that very specific scientific application, which does require specific extra funding. And oftentimes, it used to be the case that there were cracks over there where someone will fund you to do X, but these guys don't think that is their job to find dark matter. They'll go and tell you, go get money from somewhere else to get money for this. So what has been helpful in this game is that a number of private foundations have stepped in, like the Simons Foundation, the Heising-Simons Foundation, the Moore Foundation, all these guys who basically are willing to sort of get into that area, but they look for the fact that, yeah, there is actually pretty good reasons to think that if you spend money here, I might actually be able to use this technology to find some fundamental physics parameter. So they have come in very helpfully to initiate some of these applications. And once that has actually happened, that has actually helped stimulate the government also to move into this area and, sort of like start funding these things. So I think today it is in fact the case that due in part to, there's a number of activity going on in the government about building quantum technologies overall. And that has overall led into a pretty substantial infusion of funds everywhere. And some of that has also been directed now into this kind of dark matter research, things of this kind.
In the field of astronomy and cosmology, there's a bit of a renaissance going on, mostly around the Hubble constant and this idea of the crisis in cosmology, that the measurements of the expansion of the universe more recently and the measurement as it is in the cosmic microwave background differ, and yet the error bars have reduced to the point that they don't overlap, and so there is something wrong. There's something with the standard model of the universe as we understand it that is insufficient to explain it. And this is exciting. You talk to any cosmologist, you talk to any astronomer, and they are stoked that they have a crack that they can now wedge in and start to try to understand more about the fundamental nature of the universe. Particle physics seems stuck, that the Large Hadron Collider has been grinding away. testing these individual theories, as we talked about, do you think that the particle physics community is ready for a revolution, and where do you think that starts to help?
That's a great question. So here's how I view this problem, right? So yes, you are correct that particle physics seems stuck. Now, there are two issues with this, right? One is that if you think about particle physics, right, all the problems that we were inspired by, like what is the nature of dark matter? What is dark energy? Why is the Higgs where it is? Why is the universe expanding at the rate at which it's expanding? What solves the black hole information problem? None of these problems have been solved, right? Like, yes, it is true that people, had certain ideas on how to approach them, and those ideas unfortunately didn't pan out. But the problems haven't gone away, right? So this is now the problems that our generation has the ability to go and tackle. So I look at this in the following way, as a young person in the field, right? Let's think about this following very interesting issue. What is it that's difficult about a young person making progress? The difficulty is that the old people know a lot. They've already been in the field well before you, so they have all the technologies in the world to go and attack a problem that you do not yet know how to tackle. But now notice the interesting fact that in this particular area right now, you are in a very interesting situation where the old guys don't necessarily know anything better than you do, right? Because they were trying to find certain things and those things didn't pan out. Great. So you are now at the same level as they are, and you are not sociologically depressed because your ideas didn't pan out. So you are an enthusiastic young person who can play this game just as well as any of those. Terrific time to be a young person in the field and sort of do really innovative work. And for me, like, I'm always motivated by these things on how to do this. The second question that you asked is about, like, how do you make progress in particle physics, right? Like, what is it that really is necessary? And this is because physics, I would say, is really like a two-dimensional plot, right? So in a sense, we know there is dark matter. We know there's dark energy. We just don't know what they are. So think about this following issue, right? When I say there is a new particle in the world, there are two parameters that are of interest to me. First is the mass, the energy that I need to go in order to look at the stuff. And the second is basically the coupling, how strong this particle is in talking to us. Now, particle colliders have done a great job in the last 100 years of probing a variety of physics. But what particle colliders are doing is basically they're going in one dimensionless axis. They're going to more and more energy, higher and higher mass, but the range of couplings, strengths that the particle collider can probe is very narrow because they only have so many particles that can collide per second, which basically means their ability to produce particles that have extremely small couplings is very limited. So they have only, in some sense, probed physics in a one-dimensional plot, going more and more in energy, but not much in coupling.
So sorry. So I just want to understand this. Sorry, I apologize. So you're saying, like, if you would say run your particle accelerator at lower energies, but maybe more collisions, you could, back to that wind analogy, that you could detect more of a collective wind of a whole bunch of smaller, less energetic particles that would give you information on sort of a new space. Am I understanding that correctly?
Well, so actually, it's a little bit somewhat different from that. So I would say in a particle collider, right, you're sort of limited by the number of particles per second the machine can produce. So you only have so many of them. And if you want to produce a very weakly coupled particle, a very light particle, yes, what you require is to have an enormous number of collisions. You don't care so much about the energy at which you're colliding them,
right?
But you need an enormous number, okay? But it's very hard for them to produce an enormous number of these particles. That's just not technologically feasible right now. So what particle colliders do is that they get a fixed number of these particles coming out, and then they can make ways to make them collide at higher and higher energy.
Yeah, and okay. so that you could, if the particles are much lighter, it's by having a larger number of the collisions as opposed to cranking the
energy
up to produce more massive particles. Yeah. And so I was sort of saying, it sort of goes back to your original idea for dark matter. Right. And that we've been focused on the big bullets as opposed to the wind.
Exactly.
Yeah.
So here I would say, like, the issue really is that, and because it's very, very hard for a collider to increase the number of particles that's colliding, you just require newer ways of finding these very, like, weakly coupled particles. what you require are basically more and more precise technologies, right? Because these weakly coupled particles have an extremely small effect. So you want more and more sensitive instruments as opposed to just the raw power that a collider provides. So I would suggest that really we should be thinking about how do I go deeper and deeper in coupling, smaller and smaller coupling. And that is kind of where the wind is blowing now, is the sense that we are now the ability to produce extremely precise quantum sensing technologies, which we so far haven't had, right? So sort of thinking about historically, let's ask this question. How come in the last 100 years, we built incredibly amazing colliders? Why did that happen in the last 100 years? Why did that not happen 200 years ago, right? It's because of the fact that towards the end of the 1800s and the beginning of the 1900s, we as human beings, we mastered the electromagnetic force, right? 200 years ago, nobody knew anything about it. And in the last 100 years, we built the engineering to be able to crank an enormous amount of power into radio waves. That's what these colliders are really about. Mm-hmm. And that technology got us a long way, right? So as long as you gave me a fixed number of particles, I could really push them to very, very high energies. We were able to do that. Right now, the time we live in humanity, this is the time when we are really getting to that level of mastery over quantum techniques that are able to measure things very accurately, right? We're sort of beginning our exploration of extreme precision instruments. So we are, I would say, at the level of quantum technology, the same way where we were in terms of electromagnetic technology in the early 1930s, right? When people are just thinking about, well, how can I use this RF technology to do new physics? That's what, the great people of that era, like Lorentz and Chamberlain, or what those guys were thinking about. And today, I would say we are at that level where, I have really good quantum engineering. The quantum engineering is able to do very good clocks, but I have now not used it so far to go really after physics, just like how Chamberlain and Lorentz and all these guys managed to use RF technology to really go after physics.
And so maybe the next version of the Large Hadron Collider maybe doesn't produce more energy than the LHC, but gives you more particles to collide to expand the search space into those two directions.
Yeah, so it wouldn't be the LHC per se, because LHC is the wrong kind of machine to do it. It just has to be like a very quantum-inspired style. But yes, that's the kind of idea that I'm thinking about. Exactly.
Yeah. That's really interesting. So place your bets. When do you think that we will have some kind of answer for what dark matter is?
Oh, I really don't know. Physics is an interesting thing, right? Like it's basically this thing, especially in our kind of physics, right? Like it goes with its name of fundamental physics, whatever, right? So for us, things are very binary, right? Like you either discover something, discoveries are very rare, but when you discover it, it's just true. It's just true forever, right? So like it's a very binary kind of output in terms of what you're looking for, and you just don't know. I mean, like it's very hard to make a bet on whether or not in my lifetime I'll find what the dark matter is, right? Like it takes a certain kind of, I think, psychology to be okay with that.
Yeah.
Right. That I could spend my entire life looking for it, and that's fine. If I don't find it, it's okay.
Yeah. But it does feel, I mean, I you mentioned a little earlier about the string theorists who've spent the last 30 years working on their math. Nothing's panned out. And I'm sure they're having this kind of existential crisis about their lives at this point. You're going like, why did I do this?
Yes.
And maybe the lesson that can be learned is a fundamentally different way to conduct the search so that you don't rabbit hole so hard, and instead stay flexible, keep your mind open, flit from experiment to experiment, and win those null Nobel Prizes as you go, until collectively humanity knows where its car keys are. I just mashed every single analogy into one here, but yeah.
Yeah, exactly. Yeah. And unfortunately, there is no better way of doing it for dark matter, right? And there's a difference between the dark matter thing and string theory in the sense that at the end of the dark matter game, these guys look for weakly interacting massive particles for 30 years. they actually know that there is no particle called the WIMP that they look for, right? That's a true result about nature, right? They actually know for sure there isn't a particle over there. The string theorists cannot even tell you that, right? They can't actually even tell you what they don't know or what they do know.
Right.
Right? That's a big difference, because here what we know is the truth. It is knowledge.
Yeah. Yeah. So if you mentioned sort of this next generation, the young people, the people coming into physics and astronomy, particle physics, fundamental physics.
Yeah.
What advice would you give to them as they start on their journeys?
Yeah, this is exactly what I was advocating a little bit earlier, which is that they're entering this field in a very unique time where the old people have no advantage over the young people, right? It's a beautiful time to get into the community at this time when you are just as good as anybody else. And that just means that, like, essentially, for me, right, it's like whenever I look at particle physics, I see unsolved problems, I see blue sky, things that nobody has tried before. And so it's a very funny thing where people sort of get in and they're sort of a little bit depressed by the fact that the older guys are depressed, but they're like, who cares? Lots of stuff for you to do. So it's again, right, it's a little bit about the personality the person comes in, where you have to be willing to be like, yeah, this is a great time to be in, simply because the problems are so huge and the territory is so wide open that you just have to be willing to go and, take a shot in the dark and walk over there and see what's out there.
Yeah, and it's not that expensive, and you don't need to, get the government to give you a $10 billion experiment in Switzerland. There's a lot of ideas out there that nobody has really. A lot of places to look for the keys. Well, Surjeet, it's been absolutely fascinating talking to you, and I hope this gives the people entering this field and the people wondering about the search a lot of excitement and hope. If people want to follow your work, what is the best place to do that?
Follow my work. Well, I mean, I guess I don't know. I unfortunately I don't. It's pretty much my first time I have sort of had a public sort of interaction. I really enjoyed it. Thank you so much for having me.
No problem.
I don't know. I mean, like, it's sort of there have been some articles people have written about my work and that have appeared in the popular press.
Archive, I guess.
A few things, exactly. Google, I guess. I mean, yeah. I mean,
Google Scholar.
Exactly. Google. Yeah, exactly.
Perfect. Well, that's good. I think that's good. Stay away from Twitter. Get off Facebook. Just
right.
Right. Your social network is Google Scholar and Archive, and I think that will make sure that you keep your keep your head in the game. So
yeah, I'm definitely a people person. I don't hang out on the internet and yell at people on Twitter.
That's best.
I do that in person.
Yeah, perfect. That's great. Well, it's been an absolute pleasure to talk to you. So interesting. Thank you so much, and good luck. And if you do discover dark matter, would you let me know?
Definitely, you'll be the first to know.
Okay, perfect. All right, take care.
Thank you, Fraser. Thank you. It's fun.